In this video, we are going to discuss the real numbers and its properties. For that, first we are going to do a quick revision of the number system. First, consider the natural number. These numbers occur naturally. For example, 1, 2, 3 up to infinity. Then whole number. We include here 0, then the other natural numbers. Okay. Again, in case of integers, we include the negative part. Okay. Now, the rational number. We can write at p by q form, where q is not is equal to 0 and p and q are two integers. Okay. Again, finally the irrational number. Irrational numbers are like root 2, root 3, root 5, etc. Not in p by q form. Okay. Discuss about the Euclid's division lemma. Already you are familiar with the other techniques to find the HCF, but this is also a technique to compute the highest common factor of two given positive integers. So let's discuss. Consider some pair of positive integers a and b. Here we have considered 10, 3, 4, 19 and 81, 3. We can write 10 as 10 is equal to 3 times of 3 plus 1. 4 is smaller than 19, so we can write 4 is equal to 19 times of 0 plus 4. Again, here in case of 81 and 3, we can write as 81 is equal to 3 into 27 plus 0. Okay. Again, in this type of expressions, we get two new terms. The multiplying factor is called the quotient and the remaining part is called the remainder. For the first expression, 3 is the quotient, 1 is the remainder. For the second, 0 is the quotient and 4 is the remainder. And in the last expression, 27 is the quotient and 0 is the remainder. Again, if we try to write these expressions in terms of a, b, q and r, we have a is equal to bq plus r, where r is always greater than is equal to 0 and always less than b. Again, if we consider another pair 20 and 3, we can rewrite as 20 is equal to either 3 into 5 plus 5 or 20 is equal to 3 into 6 plus 2. Both are mathematically correct, but according to the Euclid's division lemma, we have to maintain this r should be greater than is equal to 0 and always less than b. This condition should be satisfied. So in the first expression, the remainder 5 is greater than the value of b, but here 2 is smaller than 3. So if we have to apply Euclid's division lemma, we have to consider this equation. So now discuss the steps to find the HCF of two positive integers c and d, where c is greater than d. The first step is apply Euclid's division lemma to c and d, so that c is equal to d into q plus r, where r is not is greater than is equal to 0 or less than b. The second step is, if r is equal to 0, then HCF of c and d is equal to d. Okay, we write in this term. This means HCF of c and d. Okay, so the condition is, if the r is 0 in this expression, this r value is 0 in the first step, then this value d is the HCF of both C and D. Step 3 is, if R is not is equal to 0, then again apply Euclid's division lemma for D and R. So if we take an example, you will understand better. Okay. Try to find the HCF of 135 and 225 using the Euclid's division algorithm. Now we have seen 225 is greater than 135. So this is our C, this is our D. Okay, because C should be greater than D. So now 225 can be written as 135 times of 1 plus 90, because 135 into 2, which is greater than 225, so we put 135 into 1. Okay, so after 225 minus 135, we have remainder 90 here. Now see, this is the remainder R, which is not is equal to 0, and this is the D. The second step was, if the R is not is equal to 0, then again apply Euclid's division algorithm for D and R. 135 is equal to 90 times of 1, and the remainder would be 45. Here again R is not is equal to 0, and this is again in terms of D. So again, if we apply 90 is equal to 45 times of 2 plus 0. So here remainder is become 0. So what we can conclude is the HCF of 135 and 225 is equal to what? 45, this value. Okay, because this is the D. Okay, so let's take this question. Show that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5, where q is some integers. There are so many other ways to prove this kind of statement, but now here we will use Euclid's division algorithm to prove this. Let us consider a is any positive integer and b is equal to 6. Okay, so according to Euclid's division lemma, a is equal to 6q plus r, where r should be greater than is equal to 0 or less than 6, because here b is equal to 6. Okay, the possible values of r would be 0, 1, 2, 3, 4 up to 5. Okay, now putting r is equal to 0, we have a is equal to 6q, which is an even number. Okay, again putting r is equal to 1, a is equal to 6q plus 1, which is an odd. Okay, because if we add an odd number to an even number, it becomes odd. Okay, putting r is equal to 3, we have a is equal to 6q plus 3, which is also an odd. At last, putting r is equal to 5, a is equal to 6q plus 5, which is also odd. As we know, q can be any integer. So let's put some q value. Putting q is equal to minus 1. Let's see what happens. A is equal to, in the first expression we put here, a is equal to minus 6 plus 1, which is equal to minus 5, which is also an odd. Okay, again putting q is equal to say 4, a is equal to, if we put in this equation, a is equal to 6 into 4 plus 5, 29, which is also odd. Okay, so this statement has proved. So our next question is, use Euclid's division lemma to show that the cube of any positive integer is in the form 9m, 9m plus 1 or 9m plus 8, where m is any positive integer. So a be any positive integer and b is equal to 3. According to Euclid's division lemma, we can rewrite as a is equal to 3q plus r, where r is greater than is equal to 0 or less than b. Here b is equal to 3. So the possible values of r is equal to 0, 1, 2. Okay. Now if we put r is equal to 0, we have a is equal to 3q. Okay. So cubing the both sides, we have a cube is equal to 3 cube into q cube. Okay, so here 3 cube is equal to 27, q cube is equal to 9 into 3 of q cube. Okay, since q is a integer, 3 is also an integer, so this whole term is also an integer. So let's say we name it m, any integer m. So we can rewrite as 9 into m. Okay, now putting again r is equal to 1, we have a is equal to 3 cube plus 1. Now again cubing the both side, we have a cube is equal to 3 cube plus 1 whole cube. A plus b whole cube is equal to a cube plus b cube plus 3ab square plus 3a square b. Okay, so if we put here 27 q cube plus 1 plus 9q, 27 q square. Okay, if we take 9 common from this term, we have 3q cube plus q plus 3 q square plus 1. Again this is an integer, we can replace it as m, so we can rewrite this as 9m plus 1. Again we have seen 9m plus 1 is a cube form of a number, of an integer. Okay, if you put r is equal to 2, you can prove that 9m plus 8 is also a cubic form of an integer. Okay, so the last question of today's video is, an army contingent of 616 members is to march behind an army band of 32 members in a parade. The two groups are to march in the same number of columns. What is the maximum number of columns in which they can march? So in this type of question, if you are asked to find the maximum between two numbers, then you have to find the HCF of that given numbers. Okay, in this case, if we find the HCF of 616 and 32, According to Euclid's division algorithm, we can write 616 in terms of 32 and with some remainder. Okay, so let's divide 616 with 32. We have here we have 19 times, remainder 8. Again, this is r not is equal to 0 and this is d. So again, so here we have remainder is equal to 0. So the HCF is 8. Okay, so maximum 8 numbers of columns which they can merge. Okay, so thank you for watching the video. Please like, share and subscribe to my YouTube channel.